Hello students, welcome to another video. Today we are going to discuss the residues. First of all, the definition of residue. Definition of residues. Definition of residues. If the congruence, if x is congruent to y modulo m, x is congruent to y modulo m, then this y is called residue under modulo m. This y is called residue of x under modulo m. If we consider this congruence, then we say that this m divides x minus y, that is this m divides x minus y. That is, we can say that if we divide this x by this number m, if we divide x by this number m, then y is remainder, then this remainder is called residue. If we take x is congruent to y modulo m, then this y is called residue of x. This y is called residue of x under modulo m. If x is congruent to y modulo m, then y is called residue. Then y is called residue of x. Y is called residue of x modulo m. Residue of x modulo m. The definition of residue says that if the congruence x is congruent to y modulo m, if we have given the congruence x is congruent to y modulo m, then we say that this y is residue. That is, if we divide the number x by m, that is, if we divide x by m, that is m divides x, then we say that this y is remainder, that is m divides x minus y means y is remainder. Whenever we divide x by m, then this remainder y is called residue. So, next definition is complete residue. Next definition is complete residue system. Complete residue system. Complete residue system. Complete residue system. The definition is the set of numbers, a set x1, x2, up to xm is called complete residue system. It's called complete residue system. It's called complete residue system. Or this called x1, x2 up to xm is called complete residue system under modulo m. xm or xn, whatever its number may be, the residue system modulo m. Modulo m. If for every integer y, there is one and only xj, there is one and only one xj, that is there is only one xj is the number in between this xj, such that this y is congruent to xj modulo m. Y is congruent to xj modulo m. Don't be confused in between these notations, that is, here we have taken x is congruent to y modulo m, and here we are going to take y is congruent to xj modulo m. This set of all xj's, this set of all, suppose xi's is said to be complete residue system. Whenever we divide any number, if we divide any number by m, then this remainder must be in between, this remainder must be an integer between this set, that is all xi's. This definition of complete residue system says us set of xi's is called complete residue system under modulo m. Whenever we divide any integer y by some integer m, then the remainder must be in between these integers. It's called complete residue system. For example, suppose if you take m is equals to 5, if we take m is equals to 5, then if we divide any number by 5, that is if we take any number congruent under modulo 5, then we must get the remainder 0 or 1. If we divide suppose 10 by 5, then we get remainder 0. So the C.R.S. under modulo 5 must contain 0. Therefore, this complete residue system, shortly we can say it as C.R.S. C.R.S. This C, suppose C.R.S. Then C.R.S. modulo 5 is must contain the first element, suppose 0, since whenever we divide 10 or 15 by 5, we get remainder 0. If we divide number 6 by 5, then 5 divides 5, so we must get then remainder 1. If we divide 6 by 5, then we get 5 divides 5 plus 1, that is remainder must be 1. If we divide 7, then we get remainder 2. If we divide 8 by 5, then we get remainder 3. If we divide number 9 by 5, we get remainder 4. Now again if we divide the 10 by 5, then we get remainder 0. Again by suppose 13 by 5, then we get remainder 3. If we divide suppose number 26 by 5, then we get remainder 1. So there is no other remainder than these 5 integers. So these all 5 integers forms a C.R.S. complete residue system under modulo m. Whenever we are going to divide any number by 5, suppose if we divide 114 by this 5, then we get the remainder 4. So all the remainders must be in between these sets. So this is the complete residue system under modulo 5. For example, suppose this first example, second example, m is equals to 3, then C.R.S. modulo 3 is C.R.S. modulo 3 is 0, since we divide 3 by 3, we get remainder 0. 4 by 3, then we get remainder 1. If we divide 5 by 3, we get remainder 2. If we divide 6 by 3, then we get remainder 0. So this is the C.R.S. modulo 3. So integers less than that m are forms C.R.S. modulo that number m. Let take one note. Note is a set of m integers forms C.R.S. This is the important note. A set of m integers, forms C.R.S. if and only if no two integers in this set, no two integers in that set, if and only if no two integers in that set are congruent. No two integers in that set are congruent. If we take some, for example, some another example of C.R.S. Suppose if we have taken here 6 in this C.R.S. under modulo 5. If we take here 6, then 6 is congruent to 1 modulo 5. So 6 and 1 becomes congruent. So that addition of 6 doesn't makes this whole set as C.R.S. So in C.R.S. these all numbers must not be congruent to each other. If any of these two numbers is congruent to each other, then we say that set of that integers not forms a C.R.S. Now next example is reduced residue system. Next definition is reduced residue system. Reduced residue system. So we are going to use the notation R.R.S. The definition is a reduced residue system modulo m. A reduced residue system modulo m is Similarly, as complete residue system, our reduced residue system is again the set of integers. Here a reduced residue system modulo m is a set of integers, is a set of integers, is a set of integers. Suppose r1, r2 to rk, r1, r2 up to rk. So set of these k integers forms R.R.S, that is reduced residue system. If that is a reduced residue system modulo m is a set of integers r1, r2 up to rk, such that this set of integers must satisfy the following condition. The first condition is residue of Ri, that is residue of every number in between these k integers, residue of every integer, that is r1, r2 up to rk with m, with this m must be 1, that is these all integers must be relatively prime to this number m for all I running from 1 to up to k. Every integer r1, r2 up to rk must be relatively prime to m. And second condition, now the second condition is this Ri, this Ri must not congruent to Rj, Ri not congruent to Rj modulo m, that is these numbers are not congruent to each other under modulo m for I not equals to j. We take 1 is congruent to 1 modulo 5, since here if we take 1 is congruent to 1 modulo 5, that is 5 divides 1 minus 1 0, 5 divides 0. So 1 must be congruent to 1 is congruent to 1, but 1 must not be congruent to any other integer in this set. Similarly, this condition is here, Ri is not congruent to Rj modulo m, where I not equals to j. For all I and j must be in between 1 to up to k, 1 to up to k. And the third last condition is residue of x and m is equals to 1. If residue of any integer with this m is equals to 1 means any integer which is relatively prime to m, which is relatively prime to m must satisfy that x is congruent to Ri modulo m, that is must, sorry here not xi, Ri, x must be congruent to Ri modulo m. Any integer which is relatively prime to m must have residue in between r1 to rk. If these three conditions are satisfied, then we say that the set of these k integer forms a reduced residue system under modulo m. Hence the definition of reduced residue system. Reduced residue system is the set of integers which satisfies these three conditions. The first condition is these integers must be relatively prime to m, that is residue of all integers with m, residue of all these k integers with m is must be equals to 1. Second condition is these all integers must not congruent to each other, that is Ri not congruent to Rj under modulo m. And the third condition is any integer relatively prime to m, then that integer must be congruent to some Ri under modulo m. Hence the definition of reduced residue system. For example, suppose if we take m is equal to suppose 12, if we take m is equals to 12, then the residues, that is if we divide any number by 12, then the remainders must be 0 to 11, that is 0, 1, 2, 3 up to 11, since these all integers which are less than 12. If we divide 12 by itself 12, then we get remainder 0. If we divide 13 by 12, then we get remainder 1. Similarly, if we divide the number suppose 23 by 12, then we get remainder 11. Any integer, if we divide any integer by 12, then we must get the remainder in between these numbers. So here the residues, these are the residues under modulo 12. These are the residues under modulo 12. Now we are going to find the reduced residue system. These all are residues, and reduced residue system must be integers in between these, since these all are the residues, and we are finding the reduced residue system. So our residues must be reduced. So first condition we are going to check is residue of R I and M is equals to 1. So we are going to find the integers which are relatively prime to 12, in integers in between this 0 to 11, that is integers, these 12 integers. Which integers in between these 12 integers? The integers which are relatively prime to 12 must be in our reduced residue system. Since residue of 1 and 12, we are going to find the integers in between this set which are relatively prime to 12. Residue of 1 and 12 is equals to 1. Similarly, residue of suppose 2 and 12 is 2, 3 and 12 is 3, 4 and 12 is again 4, 5 and 12. Residue of 5 and 12 is equals to 1. Now residue of 6 and 12 is 6, 6 divide 6, 6 divide 12. Residue of 7 and 12, residue of 7 and 12 is equals to 1. Residue of 8 and 12 is 4, since 4 divides 8, 4 divides 12. Residue of 9 and 12 is 3, 3 divides 9, 3 divides 12. Residue of 10 and 12 is 2, 2 divides 10, 2 divides 12. Residue of 11 and 12, residue of 11 and 12 is equals to 1. So these are the 4 integers, 1, 5, 7 and 11 are the 4 integers which are relatively prime to 12. So we must get the integers, we must get the reduced residue system in between these 4 integers. So second condition is that Ri. So we get a new set of integers which are relatively prime to 12 are 1, 5, 7 and 11. So we can clearly see that these integers are not relatively prime to, these numbers are not congruent to each other, since they are in between residues. And the last condition is any x which is relatively prime to m, any integer if you take suppose 13 is relatively prime to 12, then 13 is congruent to our 1. Then another integer if we find suppose 17, then 17 is congruent to 5 modulo 12. So to find reduced residue system, we first of all find the all residues, and taking those which are relatively prime to that m gives us the reduced residue system. To find reduced residue system, we must check the only first step. After that, the all the second and third conditions are obvious. So this 1, 5, 7 and 11 forms reduced residue system under modulo 12, under modulo 12. Second example, this is for m is equals to t. Second example, m is equals to suppose 9, that is find the reduced residue for m is equals to 9 is homework for you. So find m is equals to find reduced residue system for m is equals to 9, you are going to find the reduced residues, the set of all residues, that is from 0 to 8, and the integers which are relatively prime to 9, that gives you the reduced residue system. Now take one note, another note on reduced residue system is note for m greater than 0, the reduced residue system under modulo m, reduced residue system modulo m contains 5 of m elements, 5 of m elements. Clearly in the previous example of m is equals to 12, we have find that 1, 5, 7 and 11 forms reduced residue system, and these integers are relatively prime to m. So clearly these are phi of 12, that is Euler's phi function. We have seen that the Euler's phi function states that phi of m is the integers which are less than m and relatively prime to m. So clearly for any m greater than 0, the reduced residue system modulo m contains exactly phi of m elements. Now next theorem is let let GCD of A and M is equals to 1. GCD of A and M is equals to 1, and this R1 comma R2 up to Rn, R1 R2 up to Rn be a complete residue system, be a complete residue system, complete residue system modulo m, complete residue system modulo m, then ar1 comma ar2 up to arn, ar1 ar2 up to arn is complete residue system, complete residue system modulo m. If R1 R2 up to Rn is complete residue system and GCD of A and M is equals to 1, then multiplying by this a number A to each integer, that is AR1 AR2 up to ARn, gives us the complete residue system under modulo m. So we are going to prove this theorem. Proof: we have given that GCD of A and M is equals to 1. Since GCD of A and M is equals to 1, GCD of A and M is equals to 1, and this R1 R2 up to Rn is complete residue system, and this set R1 R2 up to Rn, R1 R2 up to Rn is C.R.S. modulo n, is complete residue system modulo m, that is completed. Using the complete definition of complete residue system, we can say that for all integers y there exist an element rj. Here in rj, the integer in between this set, integer rj is in between these integers. So rj, there exists rj such that y is congruent to rj modulo m. If we divide any integer y by m, then we get the remainder, and that remainder must be from this set for I running from 1 to up to n. And also by the note we can say that this ri is not congruent to rj under modulo m for I not equals to j, and these I comma j are varies from 1 to up to n. We have now, this is from given things. Now we have to prove that AR1 AR2 up to ARn is C.R.S. modulo m. So our claim is AR1 comma AR2 up to ARn is complete residue system modulo m. This AR1 AR2 up to ARn is C.R.S. modulo m. That is, we have to prove that for all y belongs to z, there exists one and only one arj. There exists one and only one arj such that this y is congruent to arj modulo m. For also arj is not congruent to some any ari, that is ari is not congruent to arj modulo m for all I not equals to j and ij varies from 1 to n. Now we are going to prove this by contradiction. Suppose on contrary, suppose ARI is congruent to ARJ modulo m, ARI is congruent to ARJ under modulo m for I not equals to j, I not equals to j. Also here we have given GCD of A and M is equals to 1. Since GCD of A and M is equals to 1, we have seen the result Ax is congruent to Ay modulo M if and only if x is congruent to y modulo M upon GCD of A and M. Therefore, by using that result, by using Ax is congruent to Ay modulo M if and only if x is congruent to y modulo M upon GCD of A and M. Using this result, we can write this Ri is congruent to Rj modulo M. This gives us Ri is congruent to Rj modulo M. Ri is congruent to Rj modulo M. But this is contradiction, since our Ri is not congruent to Rj modulo M by definition of C.R.S. This gives contradiction, which is contradiction to this R1 R2 up to Rn forms C.R.S., which is contradiction to R1 R2 up to Rn is C.R.S. under modulo M, which is contradiction to R1 R2 up to Rn to be C.R.S. So our assumption must be wrong. Hence this Ari must not congruent to Arj modulo M, and y must congruent to Ari modulo M. Therefore Ari need not be congruent to Arj modulo M. Therefore this Ar1, ar2 up to Arn must forms C.R.S. under modulo M. We have given that GCD of A and M is equals to 1 and R1 R2 up to Rn is C.R.S. modulo M. Then by using definition we have this, and to prove this we have contrarily suppose that Ari is not congruent to Arj modulo M, and by using this result we can clearly say that Ri is congruent to Rj modulo M. Hence this gives Ari is congruent to Rj modulo M gives us contradiction to the C.R.S. modulo M, that is R1 R2 up to Rn was C.R.S. under modulo M. So this gives us contradiction. So our Ari must not congruent to Arj modulo M, and this says that ar1, ar2 up to Arn forms C.R.S. This is by using the note under the definition. After the definition of C.R.S. tells us that set of M integers forms C.R.S. that if and only if no two integers in that set are congruent. Here Ari is not congruent to Arj for any I not equal to j, gives us ar1, ar2 up to Arn is C.R.S. modulo M. This is by using that note. Hence the theorem, hence the proof of this theorem. So we are going to take one more example here on this theorem. Example is show that this 0, 2, 4, 6 and 8 is C.R.S. under modulo 5. C.R.S. under modulo 5. We have seen earlier that for M is equals to 5, the C.R.S. is 0, 1, 2, 3, 4. So if you take A is equals to 2 and multiplying this every integer by 2, we get 2 into 0 is 0, 2 into 1 is 2, 2 into 4 is sorry, 2 into 2 is 4, 2 into 3 is 6, and 2 into 4 is 8. So 0, 2, 4, 6, 8 must form a CRS under modulo 5 if the GCD of 2 and 5 is equals to 1. Here we know that solution, in the solution we can say that 0, 1, 2, 3 and 4 is CRS modulo 5, is CRS modulo 5, and taking A is equals to 2 and M is equals to 5 gives us also GCD of A and M, that is GCD of 2 and 5 is equals to 1. Therefore, by above theorem, this 2 into 0, comma 2 into 1, 2 into 2, 2 into 3, 2 into 4 gives CRS modulo 5. CRS modulo 5. This is by using above theorem, which set is, so therefore the set 0, 2, 4, 6 and 8 is CRS modulo 5, forms CRS modulo 5. So, by using this result, that is GCD of A and M is equals to 1 and R1 R2 up to Rn forms CRS, then AR1 AR2 up to ARn forms CRS modulo M. We have solved this example.